Good morning all of you. Let us go for the next lectures on river engineering. As I discussed in last class, the mass conservations in three-dimensional form, we have derived it, and also we have solved few of example problems to demonstrate how to use three-dimensional form of mass conservation equations. Today we will go beyond mass conservation equations, that momentum conservation equations in three-dimensional forms. Before going that part, just like the previous class, I can see that the same three books we are referring it. Mostly these books we are following it now more details to give you the basic fluvial hydrodynamics process, what is happening it, and as soon as we will also follow the other two books as we proceed to the next chapters. As we go for the next levels, if you look at this mass conservation equations, if the flow is incompressibles, that means density doesn't change with the space and the time. Okay, the density remains constant, and that's what it happens it when the flow Mach number is less than 0.3. That's what, if you can follow any fluid mechanics book, that most of the flow we can consider as an incompressible flow in three-dimensional or two-dimensionals when the flow density doesn't vary significantly in a space and the time domains, and that's what we can find out when the flow Mach number is less than 0.3. That is the conditions we have a three-dimensional form of the continuity equations will come like this, and the two-dimensional form of continuity equations will come like this. Very simple part is making this part is 0. But we also derive the continuity equations for one-dimensional flow. That means we have only this, the variability in terms of one x directions and the time. Here h stands for this flow depth, u is the velocity. That's what, when you apply this continuity equation for open channel flow with QL is lateral flow, T is the top width, will get these mass conservation equations, the one-dimensional mass conservation equations in terms of flow depth, in terms of the velocity, in terms of lateral flow. So please refer back to the continuity equations derivations for open channel flow or the river flow with having the lateral flow part, and that's what we have a partial differential equations, what you get it in terms of flow depth, the velocity, and the QL as a function of one-dimensional in the x directions and the time part. This is what for the river flow conservation equations. To look at that further, to extend that, let's have a few examples. Okay, the solved numerical examples. Let's say you have the river, and the two sections you are measuring Q1 and the Q2. That's what is 5 meter cube per seconds, and Q2 is 3 meter cube per seconds. Assuming there is no significant change in the channel storage, there is no significant change in the channel storage, then find out the lateral flow in the reach. So that's what is happened in real field case. We can measure the velocity at the two different cross section, we can measure the flow area, we can find out the discharge at the two sections. From that, if I assume it that there is no significant change in the storage, channel storage or the plot plane storage, we can compute it a simple lateral flow part. Just let's put it in a partial differential equations form. This Q1 is given, Q2 is given, delta x also given is a 2 meter distance between these 2 points. If it that, I can find out this q delta q by delta x, the first gradient, using this just q2 minus q1 by the delta x. I am getting it this value, and the QL will be is equal to delta q by delta x minus 1 meter per second. That's what will come it as the lateral flow as we are considering this is equal to 0. So if you look at that, is a simple balancing equations, but we have put it in a partial differential equations with approximations, compute it what will be the lateral flow. It's as it's negatives, it's indicating it, that means it's a losing stream. So the same way, if I have a series of observations of the discharge at the different intervals, we can find out which is at the stretch of the river losing it or the gaining streams. That's we can do it with simple mass conservation equations following it here. Here we are following the mass conservation equations with the assumption there is not a significant change in the channel or the floodplain storage. So similar, this is a practical problems, we generally do it. Go for bit unsteady things, that example 5, in a river flow the area average flow velocity is given to for us, which is a functions of the x, okay, 10 square. The flow depth is also functions of the space x square, and the T3 is a function of the top width is a function of x, a flow area is a function of x also, and then you find out what will be the lateral flow in x and t. Now if you look at that, so that means I have a river and this is the x directions, and that x directions the u value also varies it as 10 s squares. The h, this is u value, the h also varies it with the functions with a different time interval of t1 time interval. This is h value is varying it, and that's what will be vary it, and the top width t also varies it. So that's what I am just representing you, that in a x and the t space, x and the t space, these average velocities have a functions, the flow depth has a function, top width is having functions, and you also have a flow area is a function of the x. So if you look at these problems, which is looks a very difficult, but it's not a difficult, it is a all these variable, the flow variables of velocity, flow depth, top width, area of the flow, we define in terms of x functions or the t functions. Then we try to find out what will be the lateral flow, x equal to 1 meter, t equal to 5 seconds. That means this is our governing equations. That's what it is, one dimensional continuity equation for the river having a QL lateral flow, T is a top width, and if you look at that, we can find out the hydraulic depth A by T, that's functions you can get it. You can have a partial differentiation from delta H by delta X, you can get it, and also partial derivative of H with respect to time, you can also get it the values. So just to have a partial derivatives of we are computing it as it's getting H is a function of this. So this is very simple things, we are just doing a partial derivative with respect to x or the t. The same way we are looking for the partial derivative of the velocity, that's what we have got it. Then we are, if I all this substitute it in this one dimensional continuity equations, then you substitute x value, you can get the QL value. Okay, you can get the QL value at the x equal to this and t equal to this. That means the QL, the lateral extent of the waters, it varies with the space as well as the time. That's the functional variabilities. That's the functional variability of QL in terms of space and the time. At a particular space and time, we are getting value. So that's what my point is, that again I will draw the space and time, and we are getting it the Q variations at different values. That is the relationship functions of Q1, Q2, Q3, what we are getting at functions of space and time space. That's what we are getting it this value as it's this numerical examples. Giving these examples to you give a confidence that you have a river and you have the flow measurements. If you know this functional relationship with the space domain and the time domain, we can quantify it, what could be the lateral flow. Or if you know the lateral flow, also we can quantify it, what is the upstream flow, what is the downstream flow, how the flow variable changes with the top width, the area of the flow, and the flow depth, and the average velocity. Those things we can do it with just using very basic equations of conservation equations of this. That's the very basic conservation equations, we can apply it. But this is the unsteady flow with a lateral flow. That's what we have derived it, and we can also solve these real life river flow problems adapting these simple mass conservation equations, the continuity equations for us. Now let's go for the next, which might be discussed in fluid mechanics courses. Many of the advanced fluid mechanics courses also is there. To make a completeness of this course, where I am just revising this part of the momentum equations, always I suggest you please refer any advanced fluid mechanics book, FM White fluid mechanics or Single Symbol of fluid mechanics, any advanced fluid mechanics book. You can understand it, how to derive this mass conservation equations and momentum conservation equations. Similar way the energy conservation equations. Here I will introduce you as a introductory levels to know about momentum conservation equations at the different platforms. One is the control volume at the stream tube level, another is the control volume at the infinitely small control volume, where we try to find out what could be the velocity field, what could be the pressure field. That's what is the derivations, what is called is Navier-Stokes equations for the fluid mechanics flow. So for looking that aspects, I just introduce you these conservations of momentums, which in generally we use in the river flow with very simplified forms, or also in advanced forms, like considering is a velocity field, the pressure field, accelerations field. We try to solve these Navier-Stokes equations. That's what we try to do it. As introductory, as a briefing of this concept, I will introduce to you more detail. Again, I can suggest you please refer to advanced fluid mechanics book. Let us start about momentum conservation equations. Is you know from basics thing that the force vector is equal to mass into accelerations vectors, which is Newton's second laws, talking about the relationship between any flow continuity systems, that force will be the mass into accelerations, or the force will be the mass of the rate of change of momentum part. That's the basic Newton's second laws, where here we are going to apply these same laws for a control volume like the stream tube. So this is what my stream tube, this is my control volume, where I will apply these same equations, the equation Newton's second laws for these control volumes. As I have considering the stream tube, there is a no flow cross from this, there is no flow is coming it. So there is no flow passing through this, only flow comes from this surface, goes out from this. That's the reasons we consider the stream tube as a control volume for applying linear conservations of momentum. So if I consider a stream tube, then I have a just influx and the outflux. The influx can have the resultant velocity v vectors, and u2 can have a velocity v2, and it can have the scalar components like u1 v1 and w1, u2 v2 w1. So you have the velocity vectors here coming into this, and there is no variability of the velocity here in a space domains, also the no variability of velocity from this. If you consider that part, the net force acting on these control volumes, we can also result in the three scalar coordinate directions of fx, fy and fz, and this is a space time x and yz coordinate systems Cartesian coordinate systems. Basically, we are talking about the change in the momentum flux, which is the difference between momentum afflux, means momentum going out from these control volumes, momentum influx into this control volume, that's what is coming into 3D surface and going out from this, that difference will be the change in the momentum flux. That's what we equal to the force. If I am looking for horizontal force component, I am looking the momentum flux changes happen in x directions. That's what if I substitute it rho a u y1, that means if I look at this part, if I look at this momentum flux will be the momentum flux will be the m dot v, that's what rho a v, and the velocity. So that's the components here, rho a into a to u2, that is what the momentum flux going out from this control volume coming into this control volume, that's what will be the force acting in the x directions, whereas mass influxes is given it as we are equating for the mass conservation equations we are applying for this control volume. Same way we can write for Fy and Fz. Okay. So we can find out what will be the forces acting in the y directions and the z direction for these control volumes, as if we were just writing this mass flux and change of the velocity, the scalar velocity component v2 minus v1, w2 minus w1, indicating for us what will be the force acting in the x directions, y directions and the z directions. This is a very simple way to apply conservation of momentum equations for the control volume as a steamboat tube with a influx outflux which is normal to the control surface. So that is a very easy thing, but when you come to the river flow, please remember it that you will not have a uniform velocities when you have a small channel or a big rivers like Brahmaputra or smaller river, like always you have the velocity variations. But most of the often we measure the average velocity. So we find out area average velocity. We can measure the area average velocities. If we are measuring the area average velocity, now how can I compute it? How can we can estimate it? What will be the momentum flux if I take it the variability, the variations of the velocities in a open channel flow from knowing this area average velocity part. So that what we do it, that if I am considering the velocity distributions which follows maybe a logarithmic velocity distributions, and we are assuming it is the average velocity u, area average velocity u multiplied by area will come the discharge. If I am computing the momentum flux based on this capital U and the momentum flux based on the small u, the velocity variations, if I compute it, this is actual velocity distributions, momentum flux, this is area average momentum. So we have a corrections factor, this is what we call momentum coefficient or Bosnick coefficients. That's what is a correction factors we adopt it for average velocity. If I compute the momentum flux, what will be the correction factor instead of taking actual velocity distributions? That's what we are equating it here to compute the beta. That is the momentum coefficients, and this beta values varies from 1.02 to 1.14 for open channel flow. What do we mean by this? That's what that means. If we are computing the average area average velocities and using rho u square a, you are computing the momentum flux. That momentum flux will not be actual momentum flux in open channel flow. That need a correction factors which is more than one value. That means we are under predicting the momentum flux when you consider capital U, area average velocity in momentum flux correction. That value is increases 1.02 close to the 1. That means some of the river flow it can close to the 1, some of the river it can goes to excess of 15%. So that's quite a large number of momentum flux just to have a considering the velocity variations. If you consider it, the momentum flux corrections can varies from 1.0 to 1.14 for the open channel flow. That's what indicates it. We should know it accurately, the velocity distributions, to know it what is the momentum flux coming into the control volume or going out of the control volume. If we are following average concept, we can get it these values, okay, which is under predicts the momentum flux as compared to the actual variations of the velocity in a open channel flow. Now let us commit to write the Euler equations, which is there in any fluid mechanics books, but I just to summarize you that now we are considering a small infinite small control volumes, and also we are considering that the velocity vectors which is have a scalar component, and these all are having UVW, the scalar component parts having the velocity field. They are having a variability in x, y and z, the space domain as well the time domain. If I considering the velocity field and the pressure field, velocity field and pressure field, how I can apply this mass conservation equations and momentum conservation equation. So earlier we have used the velocity field to derive this mass conservation equations. For momentum conservation equations we have to apply velocity field as well as the pressure field. That's what we will discuss here. First is very simple way that we are writing this momentum conservation equations, linear momentum conservation equations for inviscid flow. There is not significant viscous effects, or where the regions where the frictional resistance that is not that significant, the regions where the viscous is not dominated, those the regions we can apply these Euler equations. Where the viscous is doesn't dominate that much, we can have the basic equations which called is Euler equations. Now let's come back to the how I am deriving that. Again I am considering a small control volumes, as you look it, that is having a dimension of dx, dz and dy in a x, y, z, the coordinates systems. If I consider P as a pressure at this plane, at the which is just a centroid plane, and how the pressure is vary at the delta x plus by 2 distance forward or the backward, from the Taylor series I can find out the pressure variations like this. Multiplied with area, I get the force due to this pressure. So I know this pressure, I know this area of this normal surface which is dy by dz, that means I know the force. Same way what the force is acting on this, same way what is the force is acting on this. Here the force directions are given it, so we can find out the net force is acting on this control volume in the x directions. So we can have the force component due to the gravity. That's what will be the GS components of the body forces, that is the gravity forces per unit mass in the x direction. So that's this control volume having the gravity forces, but there is no frictions. This is a frictionless. There is no shear stress component here, only the gravity force components are there and the pressure force components. That's what is a gravity force which is acting in the x directions in this control volume. If I just equate it, the sum of the force is acting it in fx directions will be, this is the force acting it, as you can see that force directions, and the GS component is a gravity force. So net force is I am having this. That net force should be equal to mass into acceleration in the same coordinate directions. So if you have that part, that's what you can apply. This is the accelerations part, and this is the force per unit mass, okay, unit weight. And this accelerations part is having a two component, local accelerations and the convective accelerations in the u directions is equal to two component. One is a net force because of the pressure variations in x directions, and this is the force due to the gravity, due to the weight of this fluid element, weight of these fluid control volumes in the x direction. So this is the accelerations component, this is the force per unit mass, that is also the accelerations components. This is because of pressure difference what you have in the x directions. Because of that, what is the net force is acting it. This is the gravity force component. This is the accelerations component, as is u, and all these components we consider as a scalar fields. That's what is, we define it as a local accelerations and the convective accelerations. As I derive for the x direction, similar way I can derive for the y direction and z direction. The same way we can have these three equations, which is called the Euler equations in a partial differential forms with the scalar components of the velocity u, v, w, which is a function of the space and the time, and the pressures and the accelerations component of gx, gy, gz. That's the variabilities what we have, that we in these equations we have u, v, w, that is the scalar velocity components are unknown to us, which is a function of the space and the time, also the pressure. Four unknowns are there. Gx, gy, gz is known to us because we can see what will be the gravity force components in the x direction, y direction, z direction. So these four unknowns we can get the solution of these partial differential equations with including mass conservation equations. So three momentum equations and one mass conservation equation. The four equations, partial differential equations, if we will solve it, we will get the four fields like scalar fields like u, v, w, and the pressures. So if you look at that, nowadays lot of tools are there, computational fluid dynamics tools are there. We can solve these ones, any complex fluid flow problems, to get it what is the u variations, v variations, w variations, and the p variations. Only that we have to solve this nonlinear partial differential equation to find out what will be the u, v, w, and the p value. And this case we have a inviscity flow. Here the frictional part, the energy losses due to the frictions, or the momentum, linear momentum equations because of Poisson's terms, we are not including it. That's the reason we are talking about Euler equations formats. Let us have a few examples what you have done it for the Brahmaputra rivers using a hydrodynamic models, which is the CCH 2D models, to simulate the water depth variations at the seasonal scale, the monthly scale, and the daily scale, how the water depth is variability is there. So using these equations, when you will solve it, if you look at this is the examples file what you are demonstrating to you, water depth variations at the daily scales, the seasonal scales, and the monthly scale, which is the solutions of Navier-Stokes equations. If you look at that, we can measure the depth variations. As if you look at the scale, that how the flow depth is increasing or the decreasing, how the channels are forming it, how the flood plains are getting more waters. All these things we can do it in a mathematical models by solving the Navier-Stokes equations. That's what is today is possible is. That's what we are set up these models to find out how these water depth is variations are there, as you look at there, some of the red colors are there, the water depth has go as high of 25 meters, and there are the water depth is lesser than 3 meters. So much variability of water depth, which varies with the space, which varies at the time. That's what we are plotting it as a two-dimensional flow equations. We have solved it using these models to find out. So what I am to say that the understanding of this basic equations developing in the models, implement for the real river case, that's why it's quite challenging to know about the basic of governing equations for the river flow. Considering that we have been discussing about this, the next class we will discuss more detail how we will make it more interesting of this in terms of Navier-Stokes equation solvers. And with this, let me I conclude today classes with citing the students who are contributing for preparing these presentations and solving the problems, acknowledging their efforts. Let me have a complete this with a quote is from Mohandas K. Gandhi, is that earth provides enough to satisfy every needs, but not every man's greed. So that's what is the earth, that's what is the river process and mechanisms, water wealth. We should not be too greedy for the water wealth, but enough what is there for satisfying these human requirements or the nature requirement. With this, let us conclude this class. Thank you.